Okay, hey crew. So this is your 2D practice. As promised, these are some of the questions we already looked over, but I wanted to go ahead and hit them with you again. And some of them we have not seen yet. So this one says a river is 0.76 kilometers wide. The banks are straight and parallel. The current is 4 kilometers per hour and is parallel to the banks. The boat has a maximum speed of 4 kilometers per hour in still water. The pilot of the boat wishes to go in a straight line from A to B, where the line AB is perpendicular to the banks. And then it asks, what should the pilot do in order to do that? So we can actually see a lot of this given for us. This is the path we want to take right here. So directly across, we want to go from A to B. We know that in order to do that, we need to go diagonally because the current is going to push us. The really cool thing here is that they gave us a right triangle because these are perfectly perpendicular to each other. So we want to go straight. The current's going to push us. So in order to do that, if you think about the real world life application of it, we know that if we go into the current will push us where we want to go. So that's the triangle that we need to draw. So once again, this is what they want to happen. This is the actual. And then what I call the skew, what causes me to not actually do what I want. I did not draw a great triangle there, I'm now seeing. So I'm going to try that again. Okay. So now we've drawn this in. Now that we've drawn the triangle, we can go back and say, what do these things represent in context to this problem? So the skew is the current. Because there is a current, I can't just go straight across the river because the current would push me. If I tried to go straight across the river, then the current would push me and I would go over here. So if I tried to get in and just go straight across, the current would actually push me and I would end up going at this diagonal kind of over here. So we want to go against the current so that the current can push us. That means this is what the boat is actually doing. Those are the two numbers that we have. We kind of redraw our triangle in over here. We know that the current is 4 kilometers per hour, but so is the boat. In order to solve this, we would need to know what angle is here. So we would find out, okay, this is an x component, so we would say 4 cosine of theta equals 4. Well, if we think about that for a second and we talk about anything that we know about triangles, we know that this can't happen. And in fact, we would actually set it equal to negative because this is going in this direction and we'd be trying to find the x component going in this direction. So theta would have to be perfectly 100 and negative 80 degrees. That is what we would need to do in order for the current to push us where we need. And that is not one of our options. And that really just means this is kind of an impossibility. We would have to be going this way. And if we were going this way, the current would just be pushing us directly back the other way. We would not have a y component. So if we're at negative 180, we would not have a y component, which is what we want. So we would never be able to make it across. So this is an example of a situation that is impossible. Okay. This was our next problem. I'm going to zoom in on it for a second as we kind of talk about it. So there's a lot going on here. So starting from rest at point A, you ride your motorcycle north to point B, 75 meters away, increasing speed at a steady rate of 2 meters per second square. Then you gradually turn toward the east along a circular path, so that is going to be important, along a circular path of a radius of 50 at a constant speed from B to C, until your direction of motion is due east at C. Wow, there's a lot going on there. You then continue eastward, slowing at a steady rate of 1 meter per second until you come to a rest at point D. So I've actually taken the time to draw this in a little bit for us. So it says we start at A, and then we go north to B. So that is my north to B. And then it says you gradually turn toward the east along a circular path. So you can see I have the full circle in here. We obviously don't need this part of it. We're not doing that. I just couldn't get that to erase without erasing the whole circle. So this is the portion. This is where I'm actually going because I was going north and I need to be going east. So I need to be pointing that direction when I come out. So I did that portion of the circle. So it's my C, and now we have our D. So whenever you're doing a problem like this, it is always smart to go ahead and draw yourself a diagram. Diagrams give you a better visual of what's going on. It gives you a visual of what direction your components are in. So I highly recommend always drawing yourself a diagram. Now we come in and it says, what is your average velocity and acceleration for the trip from A to D? So because we're going from A to D, we're talking about the entire trip. Well, in order to find velocity average, that was terrible writing, try that again. In order to find VAV, we know that that is delta x over delta t. So for the entire trip, I'm going to need to know the entire delta x and the total time. Given in the problem, I'm giving some of my delta x's, but I'm not given any t. And so these are things that we're going to need to solve for throughout the problem to even answer our question. And then for acceleration average, is for average here, it would be delta v over delta t. So with the problem that has all of these different parts, I'm actually going to separate it into part 1, part 2, and part 3. Our kinematic equations only work when there is a constant acceleration. Once again, our kinematic equations only work when there's a constant acceleration. So I need to separate my trip into the 3 components that have constant acceleration. Now that I've done that, I'm actually going to create a table for myself in order to best organize my work here. Okay, so this is all the information that I'm going to need to solve for in order to get this. Something that we do need to put in is that there was 2 different accelerations given during the problem. So during part 1, there is an A that is equal to 2 meters per second squared. And because it says we're increasing, we're going to make it positive. For part 3, it says you continue eastward slowing. So I need to take into consideration whenever I'm doing anything here, there's a acceleration of -1 meter per second squared. So that is going to be useful while I'm solving, but we're not actually going to need it to answer the question. So I don't have it in the table. So once again, it's not something that I need here. So that's why I'm not putting it in my table for me. You could if you wanted to. But for me, I'm not going to because I don't need it here. However, I do know that I'll need it in order to solve some of my boxes. So now I want to put in the information given in the problem. So from A to B, it says that I travel 75 meters in the north direction. So I'm going to go ahead and say 75 north. I'm going to do everything in meters. And here we are talking about north, east, south, west. I know N could look like newtons, but I mean north because we're not talking about forces here. We're going to go ahead and keep going then. It says starting from rest, so 0 meters per second. I do not have a V final for this portion. I do not have a time. I'm not going to talk about the portion of B to C. So it says then you gradually turn towards the east along a circular path of radius 50 at a constant speed. So I know that whatever speed I started with, I'm going to end with. So these are going to be kind of the same. It's also because I'm sharing this point of B, whatever I get here is going to be that initial velocity. So we can see how these pieces tie together. Always want to see how your pieces tie together. And so your direction is due east. So it does tell me a little bit about direction. It tells me that this is 50 and this is 50 because it's the radius. At this point, because I want to know my total change in y and my total change in x, in order to find the v average, I'm actually going to include both of those. I'm going to go 50 meters to the north and I have 50 meters east because that's my total change in y and my total change in x. When we actually start solving, we're going to need to take into consideration the actual path that they took But once again, when we're trying to find the total change, we know that we just went 50 north and 50 to the east due to that being the radius. Once again, we weren't given the time. If we go in and now read about part C, it says you then continue eastward, slowing at a steady rate we gave it until you come to a rest. So the only thing we were given was that our V final is 0 meters per second. So now we have some solving that we need to do. We need to take the information that was given to us and figure out what we can do. So as a reminder, we do have an acceleration for both parts A and B and parts C and D. So as I look at this, I know that I have an acceleration, I have velocity, initial velocity, and I have delta x, and I need to find my t. So there's a handful of different ways that we could go about doing this. You could find your v final, or no, you can't find your v final yet. We need our acceleration. Sorry, this is what I get for talking to myself. So the equation that we know that we can use, there's probably different ways to go about doing this, but I'm going to use this one, is I want to find my time first here. So I can use the formula delta x equals v naught t plus 1/2 at squared. I can do this because I have everything but t. So I can say delta x equals, well, v naught was 0, so that cancels. 1/2, my a was 2, and then I can find my t squared. Oh, and I'm sorry, I can actually plug in for delta x now. So when we solve that, we end up just getting the square root of 75, which is 8.66. So I know that the time here was 8.66 seconds. Once again, I started with that because I knew I had this formula and I knew the only thing I didn't have was time, so I was good to go. Now that I have time, I can say, okay, well, I know that V final equals V naught plus AT because I need to find my V final. So I can say V final equals 0 plus 2 times my time, and that's going to give me 17.32. We were going in the north direction here. Now I can come over, and because that is what I started with for point B, I can actually go ahead and say that. North, I'm going to say my final is 17 meters per second to the east because I am taking into consideration all of my directions. And I know that I started for part B, I was going north, and then I ended east. So just my beginning and my final there. Now we need to be able to find the time it takes me to do that. So I'm going to come down here. So I have initial velocity. I know that my acceleration here is equal to 0, and I can figure out my delta x. So we can say delta x is simply equal to v naught t. Now, when we're solving this, it's going to be important that we're taking into consideration the actual path that was taken. So his speed doesn't change, so I need to know what was really the distance that he went, because we know that it's the same speed all the way around. So I just want to know how long it took him to do that. Well, looking, I see that that's really a quarter of a circle. So I'm going to say delta x is equal to 2 pi r over 4, because that's the quarter of the circumference of the circle. Well, the r we knew was 50, so we can once again say delta x equals 2 pi 50 over 4. So our delta x ends up being approximately 78.5 meters. That hasn't really given me everything I need yet because I know that I'm solving for time. But the reason why I did this is because I wanted to use this equation. So I have my delta x. So I say 78.5 is equal to 17.32 times time, giving me a time of 4.53 seconds. So once again, every time we're trying to tackle what information do we have, how can I solve for what I need? What information do we have? How can I solve for what I need? So if you look at the last part, we actually know that we have this 17 again because throughout this entire time, his speed has not changed. we had an acceleration of 2, and now we have acceleration -1. But here, and we're talking really about the tangential because we know there is some centripetal to go in that circle motion. But in order along the path, so in the tangential direction, there was no acceleration. That is why our speed has not changed again, but now it's going to. So I have a v initial, a v final, and acceleration. And there's a handful of things that we could go ahead and find here. First off, I know that v final equals v initial plus at, so I could find the time. When we do that, because our acceleration is simply 1, that becomes 17.32 seconds as well. I also need my delta x. Well, I can use my time now, but I could still find delta x using just what I had. I know that v final squared is equal to v initial squared plus 2a delta x. So once again, 0 squared is going to be equal to 17.32 squared plus 2, -1 delta x. And when we do all of that math out, we get approximately 150. And that is in the east direction because for this portion, once again, we are talking about from C to D, we are going east. We now have done the brunt of this problem, was using our kinematic equations to solve about everything that we could possibly know for each of the 3 parts. But now we actually have to answer the question, what is our average velocity? So V average is going to be equal to delta x over delta t I plus delta y over delta t j. So that is where our velocity is going to be, our velocity average. So in the x direction, if we think about our coordinate plane, x is east and west. So I want to know everything that was east. So that gives me 50 and 150, which is 200. Y would then be my north to south. So in the y direction, I have 75 and 50, which is 125. This is where most people go wrong, is they're not sure how to split up the time. They try and figure out, how much time was spent in this portion of it, how much time was spent here, and how much time was spent here. But when we're finding the average, we're talking about the total. So even though over here, we're only going in the x direction, we still have average velocity going on here because my paths start in the north direction. Time is scalar, the direction does not matter. And so we want to make sure that we use the same over all of it. So if I actually add up those numbers, 8.66 plus 4.53 plus 17.32, we get 30.51. So I'm going to divide both of these by 30.51. And we get a V average of 6.56I plus 4.09. That's a 9. Ha. Sorry about that. Technology is hard sometimes. J meters per second. Okay, we're not done. Crazy, right? Sometimes problems can just be never ending. We also need this. That was actually the easy part. My final velocity is 0. My initial velocity is 0. So here we're going to do 0 over 0 over our 30.51. Well, 0 over 30.51 is 0. So we actually have an average acceleration of 0 meters per second. And that just comes down to that definition and that final minus initial. The rest of these, what is your displacement in your trip from A to C? So you would just add up, your parts here. You have 75 plus 50 in the north, so 125 north, 50 east. What distance did you travel for the entire trip? You would see for distance, you would actually add up. Remember that in here, it was at 78. So when it's asking for the distance, it really wants to know what was the, how long was your path. And so you would add up all of your numbers, but here you would do your 78.5. So always take into consideration, is it asking for displacement or distance? So that would just be finishing up that problem really quickly. Okay, I love that problem. It's intense and there's a lot of different parts, but I think that it really shows how you can tie all of your equations together. And notice that we always use just some kinematic equation. It is really important to feel comfortable with those kinematic equations so that you're ready to jump in and use them whenever you can. This is the problem that we've not gotten to yet, and I do want to hit it with you guys because I think it is an extremely important problem as well. It makes you do some critical thinking along the lines of projectile motion. So, an archer fish launches a droplet of water from the surface of a small lake at an angle of 60 degrees above the horizontal. So, we have our horizontal. And we know that this is our initial velocity vector. So 60 degrees above the horizontal. He's aiming at a juicy spider sitting on a leaf 50 centimeters to the east. So my x is going to be 50 centimeters. On a branch 25 centimeters above the surface of the water. So my delta y then is going to be 25 centimeters. The fish is trying to knock the spider into the water so that the fish can eat the spider. What must the speed of the water droplet be in order for the fish to be successful? So we're trying to figure out what must the speed of the water droplet be? So we're trying to find this V naught. Well, just like any projectile motion problem, we need to separate this into delta x and delta y. So we actually don't have a lot of information here, but we can have a little bit. So we have our delta x and our delta y. I'm going to make it 0.5 and 0.25 because we know that the only acceleration we have here is gravity, which is negative 9.81 meters per second squared. And the x direction, it's always going to be 0. And then we can say that v naught x is the big V naught cosine of 60. And then v naught y is the big V naught sine of 60. And that's just those components. We can also say that we know that delta x is equal to v naught cosine of 60 times t. And then delta y is going to be equal to v naught sine 60 t minus 1/2 9.81 t squared. So I went ahead and put in that negative because we know that gravity is pulling down versus velocity going up. So we want that negative to be in the opposite direction there. I don't have enough information to solve here for any of them. For both of them, I don't know V naught and T. I don't know V naught or T. But I do have a systems of equations. So systems of equations are really useful when we're solving upper level math. We're going to use them all the time in Physics C. So you need to become comfortable with creating as many equations as you can and then thinking about what information do you have and what information can you find. So this one is the simpler one, so I'm going to solve for T there. I'm going to say 0.5 is equal to V naught cosine of 60 times t. I'm going to isolate t so that I can plug it into my delta y. Once again, I'm going to isolate t so I can plug it in. So that tells me that t is equal to 0.5 over v naught cosine of 60. At this point, it's really important for us to actually go ahead and evaluate cosine of 60. Luckily for us, cosine of 60 is just 1/2. So we end up with 0.5 over v naught 0.5. Those 0.5s cancel, leaving us with 1 over v naught. So the time it takes for this to happen is 1 over v naught. And remember that time is the same for delta x and delta y, is the one thing that really ties together projectile motion. With that being said, I can now plug that in to my delta y. I can now say that delta y, which I'm going to back up, delta y we know is 0.25. Instead of writing t, I'm going to say 1 over v naught, because we just said that up here that's what t is equal to. That's also 1. I didn't draw that very well. Minus, well, 1/2 times 9.81 is 4.0, nope. 905. And then instead of t, once again, I'm going to do 1 over v naught squared. Now, the only variable that I have is v naught, so we can actually go ahead and solve for it. Here, they just cancel. Sine of 60 is root 3 over 2. If we do just a little math here, so 0.25 minus root 3 over 2. I am using my calculator here. We get negative 0.616 equal to negative 4.905, 1 over v naught squared. So I'm going to divide by that negative 4.095. And there we have it. V naught is equal to 2.82 meters per second. So the really cool thing that I liked about this problem, and bonus, you guys can try and do this part. I will tell you the correct answer is falling. But why I like this question so much is because it requires you to figure out your delta x and your delta y and then how they relate. So often we have enough information in the delta y to actually solve for time, but here we didn't know anything about velocity, and so we needed both either the velocity or the time to fully solve the delta y category. So we had to use the delta x and use that system because we knew that v naught and time were the same exact value in both the delta x and the delta y category. So this is just a glimpse of some of the other types of problems that you could be doing with two-dimensional kinematics. So when we're talking about two-dimensional kinematics at the APC level, these are the types of questions that we are talking about.